Dear students, I would like to welcome you in this initiative of Department of Higher Education, Government of Madhya Pradesh for developing e-content for postgraduate classes. This is the lecture for M.Sc. 3rd SEM Physics students, and this is the 4th paper with a paper titled Atomic and Molecular Physics. Before I move forward, I would first like to introduce myself. I am Dr. Seema Hardikar, working as Professor Physics in Sarojini Naidu Government Girls PG Autonomous College, Bhopal. As I told you, we will be talking about the 4th paper of M.Sc. 3rd SEM Physics with the paper title Atomic and Molecular Physics. In this lecture specifically, we are talking about the first unit of this paper, and in that first unit also our main focus would be about the concept of NMR spectroscopy. Students, before proceeding on with the lecture, I would like all of you to have a general idea about the magnetic effect of electric current. So also, you should have an idea about what is spectroscopy. And why I want you to know this is because you have studied full paper in spectroscopy in SEM-II. Other than that, for studying spectroscopy, you have to have a basic knowledge of quantum mechanics. So these three things are prerequisite before moving on with the course. After completing this module, you will be able to understand a lot about NMR spectroscopy. Now, what is spectroscopy? The principle of spectroscopy. It is a technique that uses the interaction of energy with a sample to perform an analysis. The data that is obtained from spectroscopy is what you call as the spectrum. And what is a spectrum? It is basically a plot of the intensity of energy detected against the wavelength, mass, momentum, frequency, etc. of the energy. That means you plot a graph. I will show you in the further slides how to do that. But you should have a general idea of how you plot a graph. You have a y-axis on which you will be plotting the intensity of the energy, of the electromagnetic energy, of the radiation that are being incident on that sample. And on the x-axis, of course, you will have an independent variable which you will be varying. A spectrum can be used to obtain information about atomic and molecular energy levels, molecular geometries, chemical bonds, interactions of molecules, and other related processes. If you use this spectroscopy for identifying the components of the sample, then you call it as a qualitative analysis. On the other hand, you can also use it to measure the amount of material in the sample, and then you call it as the quantitative analysis. Now, again, look at this block diagram which clearly explains how the spectroscopy is done. You have a source of electromagnetic radiation, and then you have the sample, which can be either in a solid, liquid or gaseous form. And you make these electromagnetic radiations incident on that sample. And these radiations then pass through the sample and move on to the detector. If 100% transmittance is seen in the detector, then you say there is no spectrum as such observed. But what happens is, depending upon the charge, the motion, the spin of the nucleus and the electron, the energy with which the molecule is vibrating or rotating or whatever it is. The interaction of electromagnetic wave takes place with the matter. And when this electromagnetic radiation is made incident on the sample, we see that all the wavelengths pass through and there is no change in intensity of electromagnetic wave, but only one single wavelength is absorbed and the intensity falls, as you can see in the graph. And that is what you call as the spectrum of that sample. And you analyze this spectrum and identify or elucidate the structure of the molecule. Now, before moving forward, children, you should know the basic of electromagnetic spectrum, and so also you should know what matter is, because these are the two important things that you will be dealing with when you deal spectroscopy. So what are electromagnetic radiations, or what is electromagnetic spectrum? Broadly speaking, as you can see in the graph that I have been drawing on the slide, look at the wavelength, how it is moving towards the larger side as you move from left to right. And look at the frequency, how it is moving towards the higher side as you move from right to left of your screen. Yes, it is a very broad spectrum. And visible light, of course, forms a very small portion of this spectrum, as you can very well see over here. Now, the question arises, you have different kinds of spectroscopies. Like you have the molecular spectroscopy or the vibrational spectroscopy. All these spectroscopies you have studied in SEM-II. Which part of the electromagnetic radiation is to be used is very important. You see, as you can see in the boxes that I have drawn on the slide, just talk about the radio waves. What is the wavelength of these waves? It ranges from certain meters to 1 centimeter. And what is the frequency? It is very, very low. And what does low frequency mean? It means very low energy. Yes, I know you remember the formula E is equal to h nu. The frequency and energy are directly proportional to each other. So what is going to happen? The low energy of this radio waves is just enough to bring about changes in the spin of the nucleus. Why I am stressing on this radio wave region is because in this unit you are studying NMR spectroscopy. So we are only interested in this portion of the electromagnetic spectrum. Although I have drawn this electromagnetic wave in front of you. Now what is it? It basically is composed of oscillating electric and magnetic fields. Can you see the electric field drawn in red and the magnetic field drawn in blue? And what is the direction in which this electromagnetic wave moves? It moves forward in a direction which is perpendicular to both the direction of oscillating electric and magnetic field. Now there are certain things which you would be using while studying spectroscopy, of which you should be very particular with the wavelength. You should be able to define a wavelength of a wave, which you, I hope, already know is the distance between either two crests or two troughs. You should be very well versed with what you understand by the frequency, which you measure in cycles per second. You should also know another important parameter of this electromagnetic wave, which you call as the wave number. And what is the use of this wave number? As you all very well know that the wavelength is measured in angstroms, and 1 angstrom is 10 to the power minus 10 meter. So if you go upon measuring the number of or finding out the number of waves in say 1 centimeter of a unit, then you will find there are number of waves in that particular unit. So wave number is usually preferred over wavelength. Now how does this process actually take place, students? You make the electromagnetic radiations incident on the sample. The sample possesses a certain amount of energy. For example, the molecule of a sample, if you talk about it, is having a rotational energy. That is, the molecule is rotating around the center of mass with a particular amount of energy. And Max Planck suggested this in the year 1900, that this energy is quantized. Meaning what? That a particular molecule can rotate with a particular amount of energy. Let us suppose the value of that energy is E1. Now you make a certain incident electromagnetic radiation on that sample. If the energy of that radiation is such that it is able to move the molecule to higher allowed energy state, only then the molecule will absorb that energy and you will observe a spectrum. That means the frequency of the incoming incident wave should be equal to delta E upon H Hertz. The significance is that if we take a molecule in energy level E1 and direct on it a beam of radiation of frequency nu, only then the molecule will rise to a higher energy level E2. Now this is very important, not only from the point of view of rotational spectroscopy, but every spectroscopy. It will be followed in NMR as well. Giving you the general overview of NMR spectroscopy, it was first developed in 1946 and later physicists and chemists began to apply this technology and developed a branch of organic chemistry which is used to determine the detailed chemical structure, and that too of the chemicals specifically that were to be analyzed. Another well-known product of NMR technology, students, is very commonly known and is known as MRI, used extensively in medical fields. What is the principle of NMR spectroscopy? Nuclei of all elements carry charge. Do you know the charge on the nucleus? Yes, the nucleus is positively charged. When the spin of protons or neutrons comprising these nuclei are not paired, very important, the overall spin of the charged nucleus generates a magnetic dipole, and the magnitude of this dipole is the fundamental property of the nucleus called the nuclear magnetic moment. Here, the nucleus behaves as a single entity. In quantum mechanical terms, the magnetic moment of the nucleus can align itself parallel or anti-parallel with the externally applied magnetic field. Let us move on to certain basics of NMR spectroscopy. Before you understand how the nucleus spins on its own axis, you need to have a general idea about how the electron spins. Do we all know that the electron not only moves around the nucleus in circular orbits, but it also spins on its own axis? Now, the direction of spin of the electron can be anti-clockwise, it can be clockwise also. And this spinning of electron basically creates a magnetic dipole. Magnetic dipole means you will have the electron behaving like a magnet, having a north pole and a south pole. Now, to find out the direction in which the electron is moving and how the magnetic field is created or to find out the direction of the magnetic field created, you need to know the right hand thumb rule. Now what does this right hand thumb rule say? If you curl the fingers of your right hand in the direction of conventional current flow, that is flow of positive charge, then your thumb would point in the direction of magnetic field, that is the North Pole. Now look at this electron moving in an anti-clockwise direction. When I talk about the electron moving in anti-clockwise direction, I am talking like this. And then the thumb should point out in the direction of, and let me wait for a second. I'm talking about electron which is negatively charged particle. So the thumb would not point in the direction of North Pole, but it would point in the direction of South Pole. On the other hand, if I talk about the electron moving in a clockwise direction, then obviously my thumb would point along the North Pole. Applying the same in nucleus. Nucleus moving anti-clockwise and nucleus moving clockwise. But the difference between electron and nucleus would be in a sense that nucleus is positively charged. So when I curl the fingers of my right hand, it is in the direction of conventional current flow and my thumb would point in the direction of North Pole. Now as we all know, spin angular momentum is roughly, just an analogy from classical mechanics where you have simply the angular momentum, linear momentum. When you talk about in rotational, you have the angular momentum. And mind you, spin is a kind of factor which does not have an analogy in classical mechanics. And that is the reason why you might be remembering when we talked about the quantum numbers, the spin quantum number, or for that matter, the orbital quantum number, all these things we have been talking about in quantum mechanics vector atom model. Many of you might be remembering the third year physics. And since we need to study the spin of electron and nucleus, you should know the spin quantum number. You should have a rough idea about the spin quantum number. And I have written small s and capital I. Small s corresponding to the spin quantum number of the electron and capital I corresponding to the spin quantum number of the nucleus. And what does this spin quantum number do as far as the electron and nucleus is concerned? It simply defines the spin angular momentum of the electron and nucleus. And this idea was given by Gottsmith. And the spin angular momentum for the electron is given by capital S is equal to under root of S into S plus 1 H cross. I would just want you to just turn over the pages of your vector atom model and you'll get this formula over there. Now talking about the spin of electron, of course we all know it is 1 by 2. So if you substitute this value of 1 by 2 over here, what are you going to get the value of S? It will be root 3 upon 2 H cross. लेकिन बच्चों अगर आप स्पिन एंगुलर मोमेंटम न्यूक्लियस के लिए कैलकुलेट करते हैं, जिसको मैंने ऑरेंज कैपिटल आई में लिखा हुआ है, तो उसका फॉर्मूला भी अंडर रूट ऑफ आई इंटू आई प्लस 1 एच क्रॉस होगा. लेकिन यहां जो आई की वैल्यू है, यहां जो स्पिन क्वांटम नंबर ऑफ द न्यूक्लियस की वैल्यू है, वो सिंपली 1 by 2 नहीं होगी. It will depend upon the number of protons and neutrons in the nucleus, and it will be the vector sum of the spins of protons and nucleons within the nucleus. यहां मैं आपको एक बात बताना चाहूंगी कि आपको कुछ कांस्टेंट्स स्टूडेंट्स क्वांटम मैकेनिक्स के याद ही रखने होंगे. जैसे आपको H की वैल्यू पता होना चाहिए, जैसे आपको H क्रॉस की वैल्यू पता होना चाहिए, जैसे आपको मास ऑफ इलेक्ट्रॉन पता होना चाहिए, जैसे आपको मास ऑफ प्रोटॉन पता होना चाहिए। इन सारों की वैल्यूज आपको ज्ञात होना चाहिए। Depicting this spin in graphical form, the reference direction has been taken as the z-axis and is the direction in which the external magnetic field is applied. Here we see the z component of allowed spin angular momentum vector for electron, and as you can see in the figure, it shows two orientations of the spin of electron with spin quantum number s is equal to 1 by 2. And what does the spin do? It precesses around the z-axis in a conical section. I hope you are remembering all these concepts from third year physics. Again, I am writing down the value of spin angular momentum for electron. And what are these magnetic spin quantum numbers? They basically express the orientation in three-dimensional space. And what is this MS known as? It is known as the magnetic spin quantum number. And what values can it have? It can have 2s plus 1 values. That means 2 into 1 by 2 plus 1. And that would amount to 2 in intervals of 1. So what are the two values that you are going to get for MS? It will be plus 1 by 2 and minus 1 by 2. Students, मैं इन सब चीजों पे बहुत ज्यादा स्ट्रेस नहीं दे रही हूं। मैंने स्लाइड्स भी बहुत ज्यादा इन सब चीजों के बारे में सिर्फ इसीलिए नहीं बनाई हैं क्योंकि आपको ये सब रिवीजन है, लेकिन फिर भी मैंने मोटे तौर पे इन चीजों को यहाँ पे इसलिए लिखा है क्योंकि इन सारे कॉन्सेप्ट्स की जरूरत आपको एनएमआर स्पेक्ट्रोस्कोपी पढ़ने के लिए होगी। और अब हमारे लिए सोचने की बात है, आप इमोजी देख रही हैं ना, spin angular momentum of nucleus I is equal to under root of I into I plus 1 H cross, which is nothing but H upon 2 pi. मैं क्या सोचती हूं, I की क्या वैल्यू होगी और Mi की क्या वैल्यू होगी? Since all electrons have a spin 1 by 2, their angular momentum has a value root 3 upon 2 units. However, it is important to remember that the angular momentum of the concerned nucleus varies from nucleus to nucleus. I की वैल्यू सारी न्यूक्लियाई के मामले में समान नहीं होगी। जैसे इलेक्ट्रॉन के मामले में आप कहते हो कि स्पिन क्वांटम नंबर 1 by 2 होता है, न्यूक्लियस के मामले में आप ऐसा नहीं कह सकते। The total spin of the nucleus is the vector sum of individual spins of proton and neutron, each having a value 1 by 2. Each nuclear isotope being composed of different number of neutrons and protons will have its own spin value. However, there is no general rule for prediction of total spin of the nucleus, but certain empirical laws have been framed for that. What are these empirical laws? The rules for determining the net spin of the nucleus are as follows. If the number of protons and number of neutrons in the nucleus are both even, then the net spin of the nucleus is 0. And mind you students, जिन जिन न्यूक्लियाई की नेट स्पिन 0 होगी वो सारे के सारे न्यूक्लियाई एनएमआर इनएक्टिव होंगे, क्योंकि अगर स्पिन ही नहीं तो किस बात की मैग्नेटिक मोमेंट, और अगर मैग्नेटिक मोमेंट नहीं तो वो कैसे एक्सटर्नल मैग्नेटिक फील्ड के साथ इंटरैक्ट करेंगे, और अगर वो एक्सटर्नल मैग्नेटिक फील्ड के साथ इंटरैक्ट नहीं करेंगे तो आपको एनएमआर स्पेक्ट्रम कैसे प्राप्त होगा? तो अत्यंत महत्वपूर्ण बिंदु है कि if the number of protons and number of neutrons in the nucleus are both even, then the net spin of that nucleus is 0, and such type of nuclei are chemically inactive for obtaining NMR spectrum. When the sum of number of protons and number of neutrons within the nucleus is odd, then these nuclei have half integral spin and they are NMR active. Similarly, when the number of protons and number of neutrons within the nucleus are both odd, such type of nuclei are also NMR active because they have integral spin. I will show you in the coming slide how this is done. Now look at this table. Number of protons, number of neutrons, the total spin of the nucleus, and the examples therein. When the number of protons and number of neutrons are both even, the total spin is 0, and these nuclei are NMR inactive. So talking about 12C, talking about 16O, all NMR inactive. और मन में सहज प्रश्न उठता है, मैडम ये स्ट्रक्चर इलुसिडेशन के लिए एनएमआर स्पेक्ट्रोस्कोपी यूज कर रहे हो ना? ऑर्गेनिक मॉलिक्यूल्स के कार्बन और ऑक्सीजन तो इंटीग्रल पार्ट होते हैं, और यही 12C और 16O अगर एनएमआर इनएक्टिव है तो मैडम किस बात का स्ट्रक्चर इलुसिडेशन? इस चीज के बारे में हम लोग आगे बात करेंगे, लेकिन हम ये टेबल पहले अच्छे से जान लें कि अगर नंबर ऑफ प्रोटॉन्स और नंबर ऑफ न्यूट्रॉन्स इवन ऑड के कॉम्बिनेशन में होते हैं तो हाफ इंटीग्रल स्पिन होती है, और दोनों ऑड होते हैं तो इंटीग्रल स्पिन होती है। तो चाहे वो ऑड इवन के कॉम्बिनेशन में हो या जो दोनों ऑड हो, उस सूरत में तो वो सारे के सारे न्यूक्लियाई एनएमआर एक्टिव होते हैं। केवल और केवल एनएमआर इनएक्टिव कौन सा न्यूक्लियाई होता है? विच इज हैविंग इवन नंबर ऑफ प्रोटॉन्स एंड इवन नंबर ऑफ न्यूट्रॉन्स। देखिए, within the nucleus, the nucleons have a strong tendency to pair, और यही कारण है कि even Z even N nuclei की ground state spin हमेशा 0 होती है. So the overall spin of the nucleus will depend upon the number of protons and the number of neutrons in the nucleus. अब एक सहज प्रश्न उठता है कि in spite of neutrons having neutral charge, do they contribute to the spin angular momentum of the nucleus? न्यूट्रॉन पे तो कोई आवेश ही नहीं होता. पर इसका उत्तर यहां लिखा हुआ है. Nucleons are both fermions which have half integral spin, and further these neutrons and protons are made up of quarks, and specifically the protons and neutrons are made up of up and down quarks. The proton being positively charged particle will give rise to magnetic moment. However, the neutron is neutral but still contributes to the magnetic moment of the nucleus. Why and how? Look at this. Can you see the structure of proton? It is made up of 2 up quarks and 1 down quark. Similarly, you can see that of neutron. It is made up of 2 down quarks and 1 up quark. The red arrows over there show you the direction of spin. Talking about the charge of proton and neutron, you would say, हमें तो पता है प्रोटॉन पे +1 चार्ज होता है, 1e चार्ज होता है, न्यूट्रॉन पे 0 होता है, और न्यूट्रॉन पे 0 होता है तो मैडम वो कैसे कर रहा है, कैसे वो स्पेक्ट्रोस्कोपी में कंट्रीब्यूट कर रहा है? वो इसलिए कर रहा है क्योंकि अप क्वार्क का चार्ज +2/3e होता है, डाउन क्वार्क का चार्ज -1/3e होता है, और चूंकि आप कहते हैं कि न्यूट्रॉन्स 2 डाउन और 1 अप से मिलके बने होते हैं तो टोटल चार्ज न्यूट्रॉन का जरूर 0 होता है, लेकिन उसके जो एलिमेंट्री, उसके जो कॉन्स्टिट्यूएंट पार्टिकल्स हैं वो चूंकि चार्ज्ड होते हैं, इसलिए न्यूट्रॉन भी अपना पूरा का पूरा कंट्रीब्यूशन जो है वो न्यूक्लियस के मैग्नेटिक मोमेंट में देता है, या इन अदर वर्ड्स एनएमआर स्पेक्ट्रोस्कोपी में देता है. सिमिलरली स्पिन देख लीजिए आप. प्रोटॉन के स्पिन की बात करो तो +1/2 +1/2 -1/2 आपको 1/2 मिलता है. सिमिलरली न्यूट्रॉन के स्पिन की देखेंगे तो आप एरो देखिए, तीनों एरोस देखिए न्यूट्रॉन में जो बने हुए हैं. पहला जो अप क्वार्क के साथ बना है वो डाउन एरो है तो -1/2, और जो 2 डाउन क्वार्क के साथ बने हुए वो अप एरोस हैं तो +1/2 +1/2, तो टोटल कितना हो गया? 1/2. अब हम आते हैं महत्वपूर्ण बिंदु पे. क्या कहते हैं? The two important elements of organic chemistry are 12C and 16O, जिनमें दोनों में नंबर ऑफ प्रोटॉन्स और न्यूट्रॉन्स इवन है. तो ये दोनों NMR इनएक्टिव हो गए. तो फिर स्पेक्ट्रोस्कोपी करते कैसे हैं? How this NMR spectroscopy is done? So it is basically done on 1H, जिसको हम फेमसली PMR यानी प्रोटॉन मैग्नेटिक रेजोनेंस स्पेक्ट्रोस्कोपी कहते हैं, या H1 NMR के नाम से भी इसको पुकारा जाता है। बच्चों, अगर एग्जामिनेशन में क्वेश्चन H1 NMR का आता है तो आपको कतई घबराने की आवश्यकता नहीं है। और दूसरी जो बेसिकली स्पेक्ट्रोस्कोपी होती है वो 13C स्पेक्ट्रोस्कोपी होती है और उसको हम 13C NMR कहते हैं। और ये हमने न्यूक्लियर स्पिन और स्प्लिटिंग ऑफ एनर्जी लेवल्स में लिखा है कि देयर विल बी 2i+1 components in each case and these components are normally degenerate in the absence of external magnetic field. That means they'll have the same value of energy. But whenever you apply an external magnetic field, then this degeneracy will be lifted up and you will have 2i+1 different energy levels. You can see I've shown it over here. You can see the magnetic moment of the magnetic dipole moment is a physical quantity that gives an idea about the magnetic strength and the orientation of the body behaving like a magnet and having a magnetic field of its own. और ये देखिए, ये है मैग्नेटिक मोमेंट ऑफ इलेक्ट्रॉन। क्या आ रही है वैल्यू? हम इलेक्ट्रॉन के लिए पहले निकाल रहे हैं क्योंकि हम अभ्यस्त होना चाहते हैं चीजों से। तो म्यू जब आप इलेक्ट्रॉन के लिए निकालते हो तो इलेक्ट्रॉन के भी हम ऑर्बिटल मोशन की बात कर रहे हैं यहाँ पे, कि जब वो सर्कुलर ऑर्बिट में घूमता है तो उसकी जो मैग्नेटिक मोमेंट डेवलप होती है वो I into A होती है। I क्या होता है? चार्ज पर यूनिट टाइम। सो E/2πr, क्योंकि टाइम क्या हो जाएगा? टाइम पीरियड 1 टाइम पीरियड में अगर वो फुल सर्कल लगाता है तो वेलोसिटी अपॉन डिस्प्लेसमेंट, डिस्प्लेसमेंट 1 फुल सर्कल में कितना होगा? सर्कमफ्रेंस ऑफ द सर्कल। So minus EV/2πr multiplied by A which is πr²। तो कितनी वैल्यू आ गई? माइनस EVR/2। ऊपर नीचे न्यूमरेटर डिनोमिनेटर में अगर आप m से मल्टीप्लाई कर देते हो तो आपको आ जाता है माइनस EL/2m where L is the orbital quantum number of that electron, orbital angular momentum of that electron. And what is this L? The value of it is MEV multiplied by R. So E is taken out, so mv cross r. Similarly, you can find out the magnetic moment due to spin motion. It is written over there. And here, when you talk in terms of quantum mechanics, that means you remove this fiction that electron is a point charge. Then along with the G factor associated, all these formula are given in your second year physics book. Please refer it over there. You should know the value of Bohr magneton also over here. I would like to concentrate myself on the magnetic moment of the nucleus. And you can see over here, we have written the mu for proton and the mu for neutron. That is the magnetic moment developed because of proton and neutron individually, I have mentioned. And so also you can calculate the magnetic moment developed by the nucleus. It is measured in nuclear magneton, and the value of nuclear magneton, children, you should remember very nicely. क्योंकि आपको न्यूमेरिकल्स करने के लिए भी इन वैल्यूज की जरूरत पड़ सकती है। अब मुझे उम्मीद है कि आपको समझ आ गया होगा कि स्पिन एंगुलर मोमेंटम जो कि एक वेक्टर क्वांटिटी है न्यूक्लियस की, अब ये शायद हम लोग चौथी या पांचवी बार फॉर्मूला लिख रहे हैं, √I into I+1 h cross, and the number of possible orientation of the nuclear spin will be 2I+1। इसका मतलब क्या हुआ कि अगर I का मान 1 आता है, कब आएगा I का मान 1? जब number of protons and number of neutrons in the nucleus will be both odd. Then Mi can have values from -I to +I, including 0 in intervals of 1. So +1, 0 and -1. Similarly, the number of possible orientations of the nuclear spin will be 2I+1, meaning if I is equal to 1/2, then Mi will be +1/2 and -1/2. I hope you all are satisfied now. और ये हम लोग ग्राफिकली, जैसे हमने स्पिन, इलेक्ट्रॉन के स्पिन के लिए ग्राफ बनाया था, सिमिलरली हम न्यूक्लियस के स्पिन के लिए ग्राफ बना रहे हैं। खास तौर पे जब टोटल स्पिन ऑफ न्यूक्लियस 1 है, उसके लिए हमने ये ग्राफ बनाया हुआ है। और आप देखिए कि किस तरीके से ये कॉनिकल सेक्शन में मूव करती है स्पिन 3 डायमेंशनल स्पेस में, एंड इट लीड्स टू द ओरिएंटेशन ऑफ स्पिन around a particular conic section with precision around z axis. तो ये एब्सेंस ऑफ एक्सटर्नल मैग्नेटिक फील्ड आप देख सकते हैं, द न्यूक्लियस कैन स्पिन इन एनी डायरेक्शन एंड इट इज कॉल्ड डीजेनरेसी। ये बिल्कुल एक बार मैग्नेट की तरह है। जैसे बार मैग्नेट को आप सस्पेंड करते हो एक्सटर्नल इलेक्ट्रिक मैग्नेटिक फील्ड में, तो वो अलाइन करता है इन द डायरेक्शन ऑफ मैग्नेटिक फील्ड, और ऐसी सूरत में द पोटेंशियल एनर्जी डिक्रीजेस, है ना। क्यों? क्योंकि हमें पता है कि इस यूनिवर्स में प्रत्येक सिस्टम जो है वो मिनिमम पॉसिबल एनर्जी में आने की कोशिश करता है। तो दिस इज द मोस्ट प्रोबेबल वे. We should remember that in case of attraction, the potential energy will decrease, and and in case of repulsion, the potential energy will increase. And this is the figure that I have drawn. Instead of magnet, now I have considered my nucleus, and look at the nucleus and look at how with the field the nucleus is aligning itself according to the rule of spin multiplicity, which we have already mentioned, and with the low field, with the field, how it gains the low energy state or the high energy state against the field. For further reading, I would like you to visit Fundamentals of Molecular Spectroscopy by Colin, and also NMR and Chemistry by J.W. Hackett. Now the time has come to assess yourself. Which of the following is true? Spin is due to rotation of the nucleus about its axis. Protons have spin but neutrons do not have spin. Spin can have integer or half integer values. Another name for spin is precision. The answer to this is spin is the fundamental quantum property of subatomic particles and does not result from their physical rotation. Many subatomic particles besides the proton have spin, including the neutrons and electrons. Spin is quantized and can take a limited number of discrete values, so C is true. When placed in an external magnetic field, the nuclear spin results in precision. I showed you in the figure how it takes place in a conical section, but the spin and precision are not the same. Moving on to the second question. Which of the following spins would a nucleus not possess? 0, 1 by 2, 3 by 4 or 9 by 2? Quantum mechanics restricts nuclear spin to only integer or half integer values. Hence, I is equal to 3 by 4 is not permitted, and so the answer is C. Thank you, students. Thanks for listening to me and trying to understand the concept of NMR spectroscopy. In the next lecture, I would explain you how this actually takes place. Thank you so much.